All right, so today we are going to continue our discussion on memory hierarchy, and today we are going to talk about cache misses and how to address them. But before we start, it's always important to remind us where we are coming from. So if you look at the evolution of process technology and the products that we have, it turns out that processor and memory right now has a 50 times or even more gap between their cycle time. So it turns out that memory is the global problem if we don't anything. So in terms of like, if we want to make architecture great again, you have to make memory architecture great again first. So one thing that we have done to make architecture great again is basically we add memory hierarchy inside our process, inside our processor, in between our processor and the main memory. So if right now you dig into your processor core, you will figure out that in addition to the conventional processing elements, we also have a hierarchical memory that contains level 1, level 2, and level 3 that based on faster memory technologies called SRAM to improve the performance of our system. And with that together, right now, because the memory is a hierarchical structure, by hierarchy means that each operation from the processor has to interact with your L1 first because it's a hierarchy. So turns out that no matter it's a read or a write, the block that you are accessing, the block that you are modifying, they must be presented in L1 first. And if you cannot find it, then you have to ask the lower level memory hierarchy to give you that. And to accommodate the block that you want to you are requesting, sometimes you might need to kick out stuff from your current sets of blocks. However, sometimes if you're lucky, then you don't have to do anything and you just kick it out. However, sometimes if the block has been updated, if you directly discard the block that you currently have in the cache, then you are going to lose the content forever. So you have to write it back first. So because it's a hierarchy, you can imagine that every layer is going to do the same thing again and again until we found the stuff we want. So that's the basic idea of hierarchical access in the context now. And we have been talking about, of course, we can build a cache that satisfy efficient data lookup as well as accommodate multiple blocks. However, if you just have a direct map cache, means that one set can accommodate only one block. Through the cache simulation that we have, we figure out that everything is going to be a mess. So it turns out right now the mainstream architecture is almost every processor has a set associativity cache, means that for each set of for each cache, we organize them into sets, and each set will contain multiple blocks that would alleviate the collision problem, and so that we have fewer amount of cache misses. However, when we try to simulate a cache, there is always an issue how to partition your memory address. So in this class, we introduced the formula called C equal to ABS, which allow you to efficiently calculate and understand the geometry of your cache so that it's easier for you to know how to partition the memory addresses. And with that, you can also do a lot of analysis regarding what kind of memory access pattern will cause the problem of more misses, or it would make things better. So that's where we are. And before we start, let's have a quick kickoff question. So, you know, it's close to the time of midterm, right? So there are many cases when I prepare the exam, but I just cannot remember, or I just keep forgetting things. So under what situation do you think you forget things easily? Can some of you share your thoughts?
Stress.
Stress? Okay. So what does that mean by stress?
I don't know. Sometimes, like when you have stress, it kind of like impairs your mental functions, such as the ability to like remember.
Okay, so in a context of computer architecture, right, we can consider the stress as like if I have too many stuff, like too many programs that I need to run, right? So then I can easily invalidate things in my cache, right? What else?
Oh yeah, kind of like on the same line. Like if we're a computer, like if we're context switching too much, too many processes, like too many things to do. Like the way I like to study is I set like 4 hours. I'm gonna only do computer architecture. Only do this instead of an hour this, an hour algorithm, an hour whatever. You know? So
okay.
Yeah.
What else? So sometimes, right, another thing that I would say, right, why the midterm is like in the third week, not in the last week? Because we don't want you to like have too many content to recap before an exam, right? So we are reducing the capacity or the working set for each exam, right? And sometimes you easily forget things because they are too similar, right? So for example, in my lab, I have Andrew and Andy, and sometimes I just like misalign each other because they seem too similar, right? So what else? Okay, all sorts of the things that may cause misses in your mind. And today we are going to see what kind of stuff would cause misses in computers. So today we are going to continue our discussion like on how to estimate the friendliness of your code when it runs on a processor with a cache. And also we are going to talk about the sources of cache misses. And then we are going to talk about with that, how can we write cache-friendly code. So last lecture, we finished at this question, right? And this is what you think at the time we finished the discussion. So 67% of you think the answer is C. So after like coming down for a night. What do you guys think now?
I thought it was either A or E.
A or E. Okay, so how do we solve this kind of question based on what we have learned so far? If you are given a code like this, what are the steps that we need to do?
Like first, like kind of like try to create a table where you write the address,
Mm-hmm.
the tag,
Mm-hmm.
the the set offset, the
Mhm.
byte offset,
Mhm.
the set offset, then the block offset,
Mhm.
and then you write okay, but it's gonna be a hit or a miss.
Mm-hmm. Okay, so you need a list of address, right? But how do you know like how am I going to partition my address into tag, index, and offset?
You use the C equal to
Okay, so C equal to ABS, right? That should come first, right? C equal to ABS. And for this cache configuration, as we previously calculated, we know 6 bits, the least significant 6 bits are the offset. And the second least significant 7 bits, they are the set index, which we would use to identify which set may contain a block. And the rest of them would be the tag that we use to compare if this is the block we want. And as you mentioned, right, the first thing is we should list the memory addresses that we are going to access. So for this pieces of a code, and based on the comment we have here, is that we are going to load AI first and BI, and then CI and DI, and finally store everything to EI, right? So based on this, what's the very first array element we are going to access here? AI, but what's the I? A0, right? We are the first we are accessing is actually A0. So based on the hints we have, what's the address of A0?
0x100.
Okay, so it's 10,000 in hex, right? So if you express that in binary, right, it's basically this string, right? And because we have 7 bits in index, 6 bits in offset, right? So that's why I have the coloring here. So based on that, what's the tag?
0001000.
Right, that's in binary, right? So if we convert it to hex, that's equivalent to an 8, right? And how about the index? 0. How about the offset? It's also 0, right? So for this one, is it hit or miss? It's a miss. Why is it a miss? Because the cache is empty, right? Suppose it knows nothing, right? So this is a miss. But when we handle the miss, what are we going to do? Fetch the whole block. So what's in a block? A1, A02, A02, A7, right? Because we have, this is a 64-byte block and each element is a byte. So we should have 8 elements, right? 8 consecutive elements, right? So here we are putting A0 to A7 into the cache, right? So now, the next one that I should access is B0, right? And its address should be this. After partition, you should get a tag and index like this. So for this one, hit or miss? It's a miss, right? Okay, so at this moment, right? So it's a miss, and it's actually index 0, the same as the previous one. So how are we going? When we deal with the miss, what are we going to do?
It's supposed to be. It's multiple sets, so.
It's a multiple way set.
Yeah, multiple ways. Like in one set, there are going to be many blocks.
Right. How many?
There's going to be
4, right? So how many have we used in set 0? 1. So we still have 3 more to go, right? So we can safely accommodate this block in the same set. So nothing being replaced. So how about So when we access C0, right, the tag is 18. Also, the index is 0, right? What are we going to do? Hit or miss? It's a miss still. But when we handle this miss, what are we going to do?
Copy the block from C0 to
C7. And do we have to kick anyone out? No, right? So you can think about like a four-way set associativity. It's like this apartment, every apartment has like 4 different rooms, right? So unless you have the 5th person who wants to get in, you don't have to kick anyone out, right? So now, when we access D0, okay, again, it's an index 0, right? So this is a miss. Do we have to kick anyone out? No, because we still have 1 room available, right? Now, when we access E0, okay, tag 28, index also 0. Hit or miss? Miss. Okay, so right now, this is the 5th one who wants to visit index 0. What are we going to do? So who are we going to kick it out? A, right? Because we are using a least recently used policy. And from the time that we access E0, A0 is the longest one that we haven't touched, right? So we have to kick it out. So at this time, we are kicking out A0 to A7. Okay, who is the next we are going to access? A1. Okay, so now hit or miss? Okay, can you imagine what's the hit rate or what's the miss rate? 100%. Everything is a miss here. Everything is a miss here, right? How often would you like to write this kind of code? You are doing this kind of stuff all the time, right? If you have multiple stops that you want to traverse, right? And you might wonder, is it really, right? Is it really that bad? So right now I'm going to show you a demo to let you know that, it's on real machines, we can actually see how bad it is. Oh, shoot. The machine that I have right now is, as I said, this is a NVIDIA Jetson Nano Tegra X1. So I do have that processor available, and I'm now running this piece of code where I do EI equal to A, B, C, D, right? This is what I do, right? And then I am running this using a program called Valgrind. So sometimes, okay, I have to say this. So sometimes, so here I'm using a program called Valgrind, and it has a tool called cache grind, which so Valgrind is a pretty useful tool, especially for detecting memory leak problem. So sometimes people don't handle the pointers correctly or don't manage to collect the used memory address correctly, then you need to figure out if you have a memory leak problem. And using Valgrind, there is a tool called cache grind. And the cache grind would actually simulate the cache behavior so that you know what's the cache performance of your cache. And the thing here is that in this assignment or in this lab, most of the time we are relying on performance counters. And there is a reason, and the performance counter is actually the most accurate if the manufacturer indeed implement the performance counters in the right way. However, most of the time, people don't actually use performance counters that often. So there are many manufacturers, I don't want to say who, right? But a lot of manufacturers, they don't actually implement the performance counter in a way that they give you a very accurate statistics if your program is really short. Because, for example, like an A company, they use a sampling mechanism that once a while, they start doing the stats for their program and sampling the states. And then, for example, I may do it like once every 1,000 milliseconds, right? And then I multiply that number by 1,000 to give you the performance counting, right? So what does that mean is that if the program is running faster than 1 millisecond, you're not getting any stats. Or if the performance is not that regular within that 1 second, right? You are not getting the right stats as well, right? So some of the processor company, like the one start with an A or the one start with an N, they do the sampling thing, right? So for this processor is by an N company, right? So I cannot trust their performance counter, so I have to use Valgrind. So, but there is a problem with Valgrind, is that it can only profile the cache hit rate and miss rate for the whole program. So what I end up doing is that if you look at the code we have, right, it's a loop, right? So if I can control the number of iterations I run, I can either not running the loop or run the loop, right? So to get the stats that I want, the demo here, I'm using a technique where in the first run, I set the loop iteration to be 0. So I just don't execute the loop at all, and I collect the stats. In the second run, I run the loop as usual. So if you subtract the stats from the normal run and the run without a loop, you will get the memory accesses and memory cache misses during that loop. So that's what a demo is trying to do. So right now, what I'm doing is I'm running this on a Jetson Nano. Let me see. Okay, so the first run, I don't have a loop. And without a loop, my data cache references is about 1.5 million. And I have about 8,000 misses. Now, in the second run, I'm enabling the loop. So if you look at that, I have like 40,000 more memory accesses, but I also have 40,000 more cache misses. What does that mean? For this loop, 100% cache misses, right? So if you don't believe me, right, you can use the following one, and it also tells you the miss rate is exactly 100%. Right. So what does that mean is that if you have a processor on NVIDIA Tegra X1, if you try to write that kind of code, your cache is totally useless, right? And your program will be really slow. So now, what if I have an Intel Core i7? All right, so let's take a look. Okay, in the very beginning, this is what you guys thought. So why don't we discuss with your friends and see what are we going to get after the discussion? All right, so let's see, what do we get? Oh, wow, after discussion, 87% of you think the answer is A. So why don't you guys, is there anyone who would like to share what changes your mind? What do you guys think? Anyone would like to share your discussion? Okay, Asher, what was you thinking before?
So I've always picked A, but the reason as to why I did that was because it's a 12-way set associativity,
Mm-hmm.
so which means that if when I put something of A, B, C, D, and E, none of none of A, B, C, D, or D or E has to be removed to make place for something else.
Right.
So as a result of that, and since I know that each double is 8 bytes
Mhm.
and the block size is 64, so I know that you can do like for every 8 traversals there will be one miss. So
Okay.
that's why.
Do you all agree with that? Yeah, so if we use the same method as we did before, right, we can actually partition the address, and then you will figure out that although they all still map to the same set, however, when we deal with E0, because we have 12 blocks available in set index 0, so at this moment, we don't have to kick anything out. So O, A, B, C, D, E, from 0 to 7, at this point, they will be in a cache. So when we access A1, this is going to be a hit. So this is the magic, right? So sometimes people love Intel processors for a reason, right? Not because it's, and sometimes, right, even though the frequency of Intel processor is not faster, you still get better performance because memory is the big part, right? So now, the next time you are going to see a miss will be the time when we entering a new block, right? So for example, previously we mentioned in set 0, we only cache 0 to 7. So when we interface with the 8th element, that's when we are going to meet another miss, right? So if you continue this sequence, you will figure out this will repeatedly showing up until we reach the end, right? So overall, we are going to have a 1/8 cache miss rate, which is 12.5%, which is the answer A in this question. All right, so If you don't believe, let's have a demo again. And this time I'm going to use performance counter. So let me see, this is the Intel processor, and right now I'm going to run the program. Oh, let's see. Okay, no such file, so I have to build it. This is problematic. Okay, so is it there? No, still not there. Okay. It? Okay, looks like we ran something, and now let's see, what do I get? Okay, I didn't see anything. Interesting. Okay. Let me run it again. Run it. Oh, here we go. Wait. No, that's not possible. Let's see. Error. Tokenizing data. Okay, let me just get it and see what's going on there. Cat. Four-way MADD. Four-way at CSV. Okay, so it looks like, okay, the last line actually has a stats, but for some reason, I don't know why it's not parsing correctly. So if you check the output, right, what it actually says that, okay, the instruction count here is about 100 million. The cycles is actually 77,000. Sorry, the instruction count is actually 100,000, and the cycles is actually 77,000. The CPI is 0.75. And the miss rate here is actually 13.8, which is pretty close to our estimation, right? 13%, and we were saying about like 12.5, so it's not too far away. And in the meantime, here I also have stats from Jetson Nano. So it's kind of interesting here. Why am I saying that the cache miss rate reported by Jetson Nano is not trustworthy? Because here in Jetson Nano, we got a cache miss rate. It's also around 14%. However, if you look at its CPI, it's 2.5. And typically, if you have a pretty smooth pipeline, your CPI should be pretty close to 1, or even, and most of the time it's lower to 1, because right now we are able to execute multiple instructions at the same time. However, here it says that on average you have to spend like 2.5 cycles, and you only have 13% miss rate, right? If you do the math, you will figure out that's not reasonable, right? So that's why I'm saying the performance counter of Jetson Nano is not that trustworthy. But for this, right, at least you should know that our estimation is actually pretty close to the reality, right? So the takeaway here is that we want to simulate the cache behavior before we write a code, or say before we really deploy the code, because we want to know if this is the better way before we actually spending money on it, right? And to simulate the code's behavior, figure out where in your code will access the memory. So typically when you are grabbing data structure from the memory, reading a file and put that into a large data structure, that's where you are going to access the memory, and generating memory addresses that the code will access, and then partition the address using the concept of C equal to ABS, so that you will know if a lot of them are going to map to the same set or not. And if there are many of them will map to the same set, are we having sufficient amount of weight associativity, right? Also, question?
Yeah, so let's say that if rather than using like an array which consists of doubles, we use arrays consisting of floats. Will that be a lot? Will that mean a lot better cache miss rate?
So if you are using float, right, because you still have the same block size, right? So you are able to get like 16 elements each time, right? Because float is only 4 bytes, right? So yes, as you said, right, you are going to get better cache performance in that way because you are only going to have a miss once every 16. However, right, there are many cases we don't want to use float because of the precision, right? So there's always a trade-off. Yes, it does have better performance. However, you may sacrifice some of the precision that you want. Sounds good? Okay, so now, the most important thing here for us is not just finding the problem, right? As an engineer, another task for us is to figure out how to address the problem. And to facilitate the finding a solution for the problem, sometimes the taxonomy is really helpful. So before we're talking about the solutions, one thing that we should keep in mind is that we should figure out why are we seeing these misses. So in the textbook or in general, we say there are 3 types of cache misses. The first type is called compulsory miss. The first type is called compulsory miss. So, Asher, have you ever heard about coherence miss?
Coherence, I'm guessing it means where you're supposed to put that thing, even though there's other space, the place where you're supposed to put that thing, you can't put it over there. Something like that?
No, but that's fine because you never heard about it, right? See, that's called compulsory miss, right? So sometimes we want you to do reading quiz because we want a compulsory miss to occur before the lecture begins, right? So compulsory means the first time miss, right? Like a lot of stuff we have been doing, right? The first time we access an element, how come your cache would know that, right? The first time I ask you about coherence miss, if you never learned that, how are you going to know that, right? So that's totally understandable and totally reasonable. It's a miss. So that's called compulsory miss. And a second type of miss is called capacity miss. So in the very beginning, we talk about why are we forgetting things? Because there are too many things that I have to handle. There are too many things that I have to learn, right? Same thing for your processor. If your program just has too many stuff for the cache to handle, for the cache to keep, there's no way your cache can keep everything. No matter how good your structure is, there's no way for your cache to keep everything. So that type of miss is called capacity miss. The third type of miss is called conflict miss. So the conflict miss means that the data that I want was previously in a cache. And a cache is not completely full with the application data. However, the data is right now a miss. So it was there before, but I just cannot keep it. So one of the most commonly seen example is that a lot of data, they map to the same set. But because of the collision, you kick the older one out, even though we still have other blocks in other ways, other sets of the cache. That's called conflict misses. You can consider it as a similar concept as hash collision. So these are the 3 types of misses. And right now, I want you to check for the Tegra X1. Why are we having so many misses? All right, so let's take a look. Okay, so in the first round, here's the distribution of our answers. So why don't you guys go ahead and confirm with your friends if you are right or the answer will change your mind. All right, so after discussion, okay, more of you think the answer is D. But can some of you tell me why 87.5% of them are conflict misses? Okay, what's your name? Okay, Arniket. Okay, what do you think?
So for the first iteration, when we access A0, B0, C0, and D0.
What kind of misses is this?
Going to be gold misses because
there's
nothing in the cache.
Okay, so they are compulsory misses, right? So those are compulsory misses, right? Do you guys all agree with that? Okay, so now.
And then now when we're gonna store E0, we're gonna kick A0 to A7. And then when we go to A1, we're not gonna find A1 because we recently kicked it. So that's gonna be a conflict miss because we missed it because we had to kick it because of a conflict.
Right. And so here's the thing, right? Only the very first access to a block is considered as compulsory misses. But now, when we access A1, the A1 was previously in the cache before, right? Although we didn't intentionally access A1, but it was there before, right? It was there together with A0 and A2 to A7, right? It was there before with its siblings, its neighbors, right? So this one, it was there before. It just get kicked out. So this is a conflict misses, right? So continuously you will see everyone else is a conflict misses, is a conflict miss until we meet 8A. A8, that's another compulsory miss. B8, that's another compulsory miss because that's a new block, right? So only the first time you visit a block in the program is considered as compulsory misses. Otherwise, everything else is a conflict misses for this pieces of a code, right? Okay, so now, what if we have a Core i7? How many of the misses are compulsory misses? All right, let's take a look. Okay, so there's two extremes of data. So why don't we discuss with your friend and see what you guys think after the discussion. All right, so after discussion, 63% of you now agree the answer is E. So can someone explain that to me? What's E? E means 100%. Can someone explain that to me? Owen, what do you think?
In this case, every miss we have is because it's like a new like entry into the set, so everything is going to be compulsory.
Okay, right. So here's the thing. So for these two questions, what I'm trying to ask is that, right? So remember, in MDOS law, we want to address the most significant problem first, right? So if we want to optimize the code, the very first thing that we have to think about what's the majority type of misses, right? So when we run the same code on Tegra processors, apparently conflict misses is the main thing we need to address. However, right now, if we move the same code to Intel Core i7, conflict misses are not even a trouble, right? The only thing that we need to address remains is actually the compulsory misses, right? So if you look at the sequence, right, the only misses we are having is when we enter a new boundary of a new block, right? And that's always the first time we visit the first element within a block. So everything else is a hit. So the remaining misses are just compulsory misses, right? So if today I'm asking you the question, right now you're given this pieces of code, I'm giving you an Intel Core i7 processor, what kind of mechanism that I should use to optimize this pieces of code? You should come up with some idea that what I need is a mechanism that can remedy compulsory misses, right? So that's why we want to do this analysis and figure out what's the main source of misses in any kind of software that we need to optimize. But for this particular question, I mean, the wording is actually trying to ask you what's the majority type of misses. So the answer here is clear. The only misses we are going to see here is compulsory misses. So that's why 100% of them are actually compulsory misses. So that's why the answer of this question is that, right? So now, let's summarize what we have learned so far. So what we have learned so far is we want to simulate the behavior of your code because we want to know how bad or how good are we leveraging the cache. And if we are not, then what we need to do is to figure out where are we getting it wrong, right? Is it because compulsory misses? Is it because of capacity misses? Or because of conflict misses? And through these two questions, we see a hardware solution to alleviate conflict misses, right? So for Intel Core i7 processor and NVIDIA Tegra processors, to be honest, their cache size are not significantly different. Intel cache is not significantly larger than NVIDIA's cache. I know it's larger, but not that large, right? But in fact, the 12 ways does help to address that problem. So if we see a code with a lot of conflict misses, the hardware-wise, one thing that you can do with the hardware is to increase the weight associativity, right? But first of all, as a software programmer, we don't want to touch the hardware, right? We don't want to modify the hardware. From a company's perspective, if I need to replace the hardware, I have to spend money, which is something unwanted from the company. So one thing we want to do is to figure out, as a programmer, what we can do to improve the performance of memory. So one of the very first things that you can probably think about is that, do I have a good enough data structure? So here I have a question. So if today I know this is the most frequently used SQL query in my application, what kind of data structure should I use to store my records? All right. So, okay, 50-50, right? So, this is like president election. So right now, no matter you are Harris or, Trump, right? Just go and debate with each other. Go. All right. So after discussion, okay, still 56-44. So more of you think the answer is A. Okay. So give me some reason. I want to hear two parties. The 56 parties, why do you think array of objects, which is on the left-hand side, will have better performance?
I was just thinking because it uses a single malloc, that means it's all going to be in one continuous memory block.
Okay, so everything is consecutive?
And that might play better with the cache.
Okay. What else? How about the 44%? 44 is significant, right? What do you guys think? Any advocator of B? Owen, what do you think? You think it's A? Okay. Anyone think it's B? Eric?
I don't know how right this is, but I thought it was B because if you were to select an average of assignment 1, for example, you could easily just take that one structure and then you could just put that into your cache and you could find an average much quicker.
Okay. So the reason why Eric advocates for B is because if you look at B, right, although it seems like we need to do more malloc. Okay, so what's the difference between A and B? So in A, that's a practice that most of the software engineering class would tell you is that, okay, especially those OOP, right? They like to say, hey, think about like object-oriented programming, right? Like a student, it should have like a set of properties, right? So we should design objects in this way, right? So A is pretty much reflecting that, right? So it's starting from students, right? So each student has a student ID, and each student should have assignment grades 1, 2, 3, 4, 5 until the end, right? So to store the record, we store students by student. So in a memory layout, it would be student ID, assignment 1 of the student 1, and assignment 2 of the student 2, blah, 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 until the end, then we wrap around to another student, right? So pretty much like a table in our mind, right? So you can easily imagine that from the software perspective, software engineering's perspective, and code is a lot easier to read. So on the right-hand side, right, if it's like a 110, well, software engineering, is it 110? Right, if it's a teacher from the 110, he would definitely give you a very low grade, right? Because if you look at the data structure, first of all, right, what are you guys doing, right? So the thing is that the data structure is pretty much like a collection of a few tables, or say a few arrays, right? The first array is an ID array, which contains everyone's ID. And then the second one is an assignment 1 array, which contains everyone's assignment. And then assignment 2 array, right? But today, if what I want to do is this SQL statement, and in fact, select by columns are the most frequently used type of SQL query, right? Should I go with the left, or should I go with the ugly right, right? So I would say the answer is right-hand side. And now I'm going to show you why. So I have a demo here, which I implemented a few data structure from the students, and it implements exactly the query that we have. And here I'm trying to take an average of one of the homework. And right now, I am going to run this piece of code and show you the difference in performance. So here's the code that we want to run. And here's the driver code that implements the select query here. And now, let's see who is better. So if I run it with the left-hand side, the array of objects, and here I'm assuming like 29K students, which is way below the number of students at UC San Diego. It takes 9 seconds if I use the one that CSE142 would suggest. However, with the other one, 3 times faster. Does that surprise you? Does that surprise you? Right? So here is another visualization, right? So if you can think about, for the left-hand side, your data layout is pretty much like this. Assume this is your memory address space, right? So when you are trying to count the average assignments, you are picking this one, and then you go to this one, right? So assuming this is a cache block, you are always going to have compulsory misses. Or you need to cache many cache blocks, right? And it's too many. So if you have many records, when you want to calculate assignment 2, it's going to be capacity misses, right? So this is not good. However, on the right-hand side, I'm basically starting with an ID array and then assignment array. So when I want to calculate the average of assignment, I'm basically sliding in consecutive addresses. So I only get compulsory misses once in a while. And if I repeatedly use the same column, I'm not even getting any misses. Isn't that better? Are you convinced? So in fact, in database systems, most of the time, people are going to use column store instead of row store. So column store means that, okay, so row store means that we store we store each record in consecutive memory addresses. So you can think about this as the table, right? And typically from the Excel's perspective, right, we think the attribute is a column and a record is a row, right? So row store means that we store row first and then column, right? And so most of the time, people would think this is more natural. However, as we just showed in the previous question, it's going to be a disaster in performance if the most frequently used query is something like select, right? So most of the time in real database system implementation, we don't use row store. Instead, we use column store, which would store each column consecutively in the memory. So you might so if you check the dumped SQL table, right? One thing you will find is that in its content, it's pretty much like this. So first of all, for this table, what we get is 001, 002, 003, 004, which is your row ID column. And then go with the last name, for example, Smith, Jones, Johnson, something like that, right? Instead of Smith, Joe, 4,000, 40,000, right? Because most of the time, the query we are using is performing better if you have a column store. So that's a very first thing that you have to think about, right, when you design your software. So depending on what's the most frequently used workload on your software, what's the most frequently used behavior of your users, you have to think about what kind of data layout would be more cache friendly for performance. So that's the first thing. And as you can see, right, if you can change the data layout or if you lay out data properly, as I mentioned, when you perform that query, you don't have to fetch that many blocks. So you are reducing the chances of compulsory misses. And if you don't have fetch that many blocks, you may also reduce the chances of conflict misses, because the more blocks that you bring in, the more blocks that you have to touch, right, the more likely you are going to have conflict misses, as well as capacity misses, because the total amount of data that you need to visit for this query or the total blocks that you need to touch is smaller, right? So this is better in all aspects. So one thing that I would think is that although it's really important to write human readable code, however, sometimes if you can pay attention to how you design the layout of your data, that would actually means a lot for your program performance. Okay, so that's the thing. Now, the second categories of optimizations we are going to talk about is the loop. So there are three things we can do with a loop: loop interchange, loop fission, and loop fusion. So loop interchange, you have seen that before, right? So if you look at version A and version B, where we traverse the loop in different order, right? We didn't change anything in the iteration. What we do is to change the order of traversal. This is called loop interchange. And now, since you already learned the theory of locality, now you already know the address sequence of memory. You should know that why version A is way better than version B, because it allows more consecutive memory accesses compared against version B, right? So this is called loop interchange, by changing the order, the level of loop traversal. Now, we are going to talk about the second type of loop optimization. So right now, as a programmer, you might interface a problem, right? I work for NVIDIA, for example, right? I cannot tell my boss saying that, hey, let's just abandon our processor and use Intel processor, right? So what you have to do as a software programmer is that I still have to make my software program perform really well on this processor. So what can we do? So now I have another version of this piece of code which will generate exactly the same outcome. Can you tell me by how much I can change the data cache miss rate to? All right, so let's take a look. Okay, so most of us think the answer is B. So why don't you guys talk to your friends and figure that out?
I think it should be more like 10%.
You use each squares.
But the thing is that the last E that you keep is you then you then have this again. So you then have to put this yeah, but the thing is that
All right, so let's take a look. Okay, see the magic of discussion. So most of you right now think the answer is A. Can some of you tell me why? Okay, Ash, you are my good friend.
yes.
I know you are.
For the first loop,
Mm-hmm.
I think there's going to be a miss rate of 12.5%.
Okay.
Because 4 sets, 4 blocks per set,
Mm-hmm.
and since one block can have at most 8 elements of the array,
Mm-hmm.
so 1 miss per 8. So the first one is 12.5.
Mm-hmm.
Then when you come to the second block,
Mm-hmm.
the E block that is there in the cache that will have to be yeah. So the E that is there already there by
Mhm.
the end of the first loop would have to be removed, and the new first one has to be put.
Mm-hmm.
Then the D has to be put,
Mm-hmm.
and then you start this process all over again, where there will be 1 miss per 8. So 1 miss per 8 again comes to 12.5. So based on that, I was like, it's closer to 10 than it is to 20.
Okay, do you guys agree with that? Okay, so let me repeat your answer again, right? So first of all, do we all agree here? Because we are just traversing 4 data structures and we have 4 different ways, right? So all the conflict misses should be gone, right? So here we have a miss rate like 1/8, right? Okay, so here, what's the miss rate? So first of all, right, if you check the code, E is probably the last accessed in each iteration because it's the one that stored the last, right? So it's the least unlikely to be kicked out, right? So E should always be the cache. Agree with that? Okay, so there's no miss here, right? However, every time when we touch a new D multiplied by 8, we are going to see a compulsory misses, right? So for these pieces of a code, right, we are seeing no misses here. We are seeing 1/8 here, right? So there is a miss rate of 1/16, right? Because every 8 iteration, you are going to see 1 miss on the right-hand side, but no miss on the left-hand side always. So it's 1/16. Question?
Yeah, for the second loop, why is EEI not going to be a miss? Because the thing is that
so as I said, right, you store to the E1 after everything is done. So it's the most recently used, and you are kicking out the least recently used.
But the thing is that the last block that was there in the first loop, that's going to be the last block. But then when you go to the new loop, you're going to get the first block. So shouldn't you?
So here's the thing, another question, right? we have 32 kilobytes. We have 512 elements to traverse. Are we going to have capacity misses? If you think about this carefully, right? For 512 times 8, right? What is that? 4K. 4 data structures we have. We only need 16K to store everything. And we have 32 kilobytes, so there's no capacity miss here. Agree? Right? Okay.
Because it was not a problem with capacity miss. It was more like if the last thing in the first loop was the last portion, the last block, the last 8 stuff. Then when you go to the second loop, you're going to again have to access the first 8 stuff.
Yeah, but it's in a different set with the last 8 stuff in the cache because you have different sets. Are you okay with that? If you check the table we had before, right? They are all in different sets. The consecutive elements, right? The first one, the first 8, they are in set 0, and then you go to set 1. If it's a different set, there's no problem of kicking others out, right?
Yeah.
Okay. Are we all good? Question?
If it's always a hit for E, which I get because you store everything and everything fits in the cache, then why is it a miss when you hit D?
Because we never access D in a first loop, right?
Oh.
Right, and that's the trick, how we avoid the 100% miss rate in a loop, right? So with this, we are actually bringing down the cache miss rate to only 10%, even though we have 4-way cache. So this kind of mechanism is called loop fission. By splitting a single loop into separate ones. Again, if you are the software engineer professor, you hate me because this makes your code harder to understand. However, sometimes, especially when you work on embedded system, you will see a lot of code like this because we want to optimize for performance. Okay, so we are talking about a few software optimizations. First of all, data layout can improve all types of misses. Loop interchange can avoid conflict misses or capacity misses if we do it right. And for loop fission is only when we have a majority of cache misses as conflict misses. Okay, so I think we are running out of time, so I will finish our discussion here. Before you leave the classroom, several things that I want to let you know. So we have a midterm next Monday in person only, and during this lecture time, and it's 80 minutes long, in person, closed book, closed note. Don't bring anything except for a calculator. And when I say a calculator, it's a physical calculator, not your mobile phone, not your computer. So if we see anything that's not a physical calculator, you should not use it other than your pen. And you cannot even bring a paper. We will provide scratch paper if you need. And we have multiple choice questions and assignment style questions on the test. So practicing the assignment and also do the assignment again by yourself will probably help you a lot. And tomorrow, I'm going to cancel the lab lecture, but I'm going to extend my office hours starting from after the lecture to 6 p.m. So if you study and you have every question in mind, feel free to bring it to me tomorrow. And the content we are going to cover is until the lecture tomorrow. So not just today, but also tomorrow, okay? And we have an update to assignment 2 because previously I was assuming integer data types, but right now I'm using like 64-bit integer. So the stride should be cut by half. So I forgot to update that one. And to update your assignment, again, go to the script in section 2.4 and refresh the browser, not your notebook, so that you can how you get the latest update. And again, our assignments are due on Saturdays because I always want you to guys to take a rest on Sundays. And also, we have a test on Monday, so you need a day at least to prepare the test, right? So that's why it always due on Saturday. And that's everything. Otherwise, I will see you later in the office hour, or I will see you tomorrow. Enjoy the rest of your day.